Hello students, in this lecture we'll see how to solve a second order partial differential equation by using the method of separation of variables. Now the steps to be performed while solving the partial differential equation are given here. The first, you are given a partial differential equation of some function. Let us say that it is a function of two independent variables. Now what is to be done is write this function of two independent variables as a product of two functions. Each function is a function of only one independent variable. Suppose a given function is a function of three independent variables, then you have to write it as a product of three different functions. Then substitute this in the given partial differential equation, simplify it, and when you simplify it, it will give rise to two ordinary differential equations if there are two independent variables. Then you can solve the ordinary differential equation by the available methods, and then you can write the general solution. In this illustration, we will see how to solve the partial differential equation using the method of separation of variables. So equation which is given is dou2 phi by dou x2 plus dou2 phi by dou y2 equal to 0. In electrostatics, we come across this type of the equation which is called as a Laplace's equation in two-dimensional rectangular coordinate. Now let us see how to solve this. Now this phi is a function of x and y. So here partial derivative with respect to x and y is there. This is because the phi is a function of x and y. So first step, we write this function phi of x and y as a product of two functions, capital X and capital Y. Capital X is a function of small x only, and capital Y is a function of small y only. Then we differentiate partially with respect to x successively twice. So when you do it, that y is a constant. When you differentiate partially the function phi with respect to y successively twice, that x is a constant, so it comes as a multiple. Then substitute those second order partial derivative with respect to x and y in the given equation. So we get this dou 2x by dou x2 y plus x dou 2y by dou y2, that is equal to 0. Now first what is to be done is we have to make each of the term. So there are two terms here. The first term contains function x and function y. Second term contains also function x and function y. Now we want to make each term containing only one function, either x or y. So to do this, from the first term we have to eliminate this y, from the second term we have to eliminate this x. So that can be done by dividing by capital X, capital Y, and when you divide that by capital X, capital Y, what you get is 1 by x dou 2x by dou x2. So this first term contains only function x plus second term 1 by y dou 2y by dou y2. So the second term contains only function y, that is equal to 0. Then you take the second term on other side, it becomes minus. So now we have is 1 by x dou 2x by dou x2 equal to minus 1 by y dou 2y by dou y2. And here we find that left hand side is a function of x only and right hand side is a function of y only. And in mathematics, whenever we have the equation where left hand side is a function of one variable, whereas the right hand side is a function of another variable, then it means that each side is constant. So now we write each of these side equal to some constant, let us say lambda, and that lambda is called as a separation constant.
In this slide, from the first step to the second step, we have replaced partial derivative by ordinary derivative. That means we have replaced dou by d. The reason for this is, in each of this equation, it depends only on one independent variable. Example, in the first equation, it depends only on x, whereas in second equation, it depends only on y. So that's why partial derivative or ordinary derivative, it makes no difference. Then we take this capital X on the other side, we get d2x by dx2 equal to lambda x, and in the second equation we get d2y by dy2 equal to minus lambda y. Then we bring what is there on the right hand side to the left hand side, and now this results into the two ordinary differential equation. So what we have done is, we started with one partial differential equation and we have arrived at two ordinary differential equation. These ordinary equations are second order differential equations, and they can be solved by using what is called as D operator.
So here on the first equation, we have replaced here d2 by dx2 by d square, and other equation we replace d2 by dy2 by d square. Then you take this x outside in the first equation and y outside in the second equation. So what you get is d2 minus lambda x d square plus lambda y. Now the next step in the here d operator is, see, this is called the method of D operator. The next step is, you have to treat this as an algebraic equation and not the differential equation. So that is a method to solve the second order ordinary differential equation. So when you treat it as an algebraic equation, so now here it is not operator. So d2 minus lambda is one term and x is another term, and this is the product of two terms. Similarly, on the other equation, this d square plus lambda is one term and y is another term, and that is the product of two terms. Then when the product of two terms are equal to 0, then both the terms are equal to 0 or one of the term is equal to 0. In the first equation, x cannot be equal to 0, so d square minus lambda equal to 0. In second equation, y cannot be equal to 0, so d square plus lambda equal to 0. And then since it is an algebraic equation, the resulting equation is the quadratic equation in D, capital D. And here you can find what is D. You can take this minus lambda other side, you get plus lambda, d square equal to plus lambda, so d equal to plus or minus root of lambda. In the second equation, d equal to d square equal to minus lambda, so d equal to square root of minus lambda, that is plus or minus square root of lambda into I is imaginary. So what you get here, the solution of that quadratic equation is imaginary second case and real in the first case. Now here one root is plus, in the first equation one root is plus root of lambda, other root is minus root of lambda. So they are real and unequal. Then the second case, the one of the root is plus root of lambda I, other root is minus root of lambda I, so it is imaginary and unequal. And whenever such unequal roots are there, then solution is given as, example for the first equation, the first equation is d2x minus lambda x equal to 0. So x equal to some constant k1 e raised to root, first root, into x, because the first equation it is with respect to x, plus k2 into e raised to second root, which is minus root of lambda, into x, because that partial differential, that ordinary differential equation with respect to x. Then for the second one, the y equal to k3 e raised to first root, which is plus root of lambda I y, because that second equation is the ordinary differential equation with respect to y, plus k4 e raised to second root, which is minus root of lambda I into y. Then what we have studied at the beginning, that phi equal to xy. So we substitute here x and y, and now this is what is called as the general solution of that given equation.